students, good evening. Welcome to this video session. My name is Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall discuss piecewise functions. This is the first part of the video. It's going to be a video playlist on piecewise functions. In this video session, we shall give an introduction. What does piecewise function mean? Give some examples of piecewise functions. And then in the part 2 video, we shall look at some real-world applications of piecewise functions. Then the next video after that, we shall look at graphing piecewise functions. So we're going to discuss introduction of piecewise functions. Then we do some videos on the applications of real-world applications of piecewise functions. Then we are going to do graphing piecewise functions, and then we are going to talk about continuity and discontinuity as regards piecewise functions. You do that in calculus. So this is a video playlist, and please follow it in order. Do not skip. View these videos in order. What we are going to discuss, you can find it on my website, any of my websites, www.samuelchukwuemeka.com or www.chukwuemekasamuel.com. Alternatively, you can go to this website, www.piecewise-functions.appspot.com. So this will contain the notes, the links to the videos, the calculators of some applications of piecewise functions, and other resources as well. So what are piecewise functions? You've heard of a piecemeal approach. Have you heard of piecemeal approach? Like step by step. Don't take it all together, step by step. Piece in pieces. When you have pieces. So we say that, and what I'm going to define, is the notes are here. So you can also write down as I'm explaining, or you can also read the notes on this website. So we say piecewise function is a function that is in pieces. You have it just the literal. The literal meaning is that the piecewise function has other sub-functions. It's a function that consists of other sub-functions, which you can call pieces, other pieces, defined over some domain or some intervals, some sequence of intervals. So piecewise function is a function that has sub-functions as pieces. Inside that piecewise function, you have some other sub-functions as pieces, and those sub-functions are defined over some intervals or over some domains. Okay, so a piecewise function is a function that contains other sub-functions defined over some intervals. Those sub-functions are defined over some intervals. And it is very important to note that the domains of each sub-function do not overlap. The domains of each sub-function inside that piecewise function, they do not overlap. You can ask your students, what if it overlaps? What will happen? If you're part of the applications we are going to do here is, not in this video though, would be writing computer programs to calculate piecewise function. So if you are writing computer programs to calculate piecewise functions, if the domain overlaps, what would happen? These are just some direct questioning techniques you can ask your students. So, you know, I know some of you probably, you might say, what is this guy talking about? So, here is the thing, okay? Anywhere you have used conditions, you know, in computer programming, we call it conditional statements. If, else if. Okay? Anywhere you've used conditions, you know, for some events or for some group of people, you've used a piecewise function. Okay, you've used a piecewise function. So let's say now, okay, hey, it is maybe you want to do for seniors over 65 years, free entrance at the park. But for some other people, you pay. You see, you've used the condition. Okay, that means that for you to enter free at the park, you must be a senior. That is a piecewise function. It is not a one size fits all. It consists of sub-functions over some conditions. So maybe they say senior living, or you must be a senior, then this house price is reduced. Otherwise, you must pay this price. You have already used piecewise function. With the car rental, okay, if you drive so number of miles in a day, then you pay this basic price. Then if you drive more than this, then you pay this per mile. You know, you have the basic fee. If you drive this mileage, this is the amount you will pay per day. But if you go beyond that mileage, you pay the basic fee plus some other money per mile. Okay, so happens in car rentals, in parks, in restaurants, in a water bill. Okay, we're going to do application in water bill, in power bill, in your cell phone bill. You know, some cell phone companies, if you're on their network, they say, okay, if you use 300 minutes in a month, this is how much you will pay. Then if you go beyond 300 minutes, you pay so amount per minute. That is a piecewise function, because it's not a one size fits all. Okay, so for this group of people that used less than or up to 300 minutes, this is how much they will pay. For this group of people that now exceeds 300 minutes, this is how much they will pay. So we use piecewise functions all the time. Anytime you use some conditions for some people or for some events, you've used piecewise function. So we are going to, we've defined it. We are going to look at a simple real-world application for this video. And then we're going to give some mathematical examples of piecewise functions. Then those mathematical examples, we'll see those and how it works. And then you watch out for more videos on applications. But let's begin with a simple application. So what I have here is the kids buffet at the Golden Corral. The kids buffet at the Golden Corral. Okay? The kids buffet meal at Golden Corral restaurant. Now they didn't pay me to, you know, they're supposed to pay me, right? Or they're supposed to give me free meals, right? So I'm not advertising for Golden Corral, but it's a nice, place. Sometimes I go there. So it's a nice restaurant, it is. So because I love Golden Corral, and I love kids, so let me say I will use a kids buffet. Okay? so they might say I'm advertising for them, right? Because I'm using their name in my video. Okay, now let's this. So if you look at some Golden Corral restaurants in the United States, they have the kids buffet, and if the website is on this website, the link. Okay, so this is what is there. Ages 3 and under. 3 and under. They eat free. And then ages 4 to 8 is $5.99 per child. And then ages 9 to 12 is $6.99. Now, this is the information I got from the website. So this might be different for some other Golden Corral restaurants. I don't know, but this is the information they had, and you can check it out as at the date and time of this recording. Okay, so this is what I have. As you can see here, folks, this is a piecewise function. Now, we also say that a piecewise function, some textbooks also call it piecewise-defined. Piecewise function. Some textbooks will say piecewise-defined function. Defined function. And some textbooks might say hybrid functions. Hybrid functions. So, some might call it stepwise. Some might call it stepwise. So as you can see here, this is a piecewise function because we don't have all one size fits all. We don't have an amount for everybody. Okay, and of course, if you're more than 12 years, if you're above 12 years old, that means you're no longer a child. All right. Now, so how do we write this? I chose this simple example just for you to really understand this concept. We have the first thing you have to do anytime you're writing functions, even in computer programming, is to define your variables. Okay, we have two variables involved here. We have the age. Let's call it A. Let our age be A. And then we have the cost of the meal. Let's call it C. So, as you can see here, C, the cost of the meal, is a function of the age of the child. I don't really like using kids. I don't know. I prefer children. Okay. Now, the cost is a function of the age. The age is not a function of the cost. Okay, when we did functions, the cost of the meal for each child is a function of the age of the child. If the child is 3 years, cost is $0. If the child is 7 years, the cost is $5.99. If the child is 10 years, then the child pays $6.99. So the age is not a function of the cost. You see that? The cost of the meal is a function of the age of the child. Now C is what we call the dependent variable. The dependent variable. And then the age is the independent variable. Because the cost depends on the age of the child. So that means that C is a function of A. And this C is a function of A. We can simply write C of A. C of A. We pronounce it as C of A. Cost of the age. Okay, cost as a function of the age. You can just write it as this. C of A. Okay, that's what it means. This is what it means. Yeah, C of A. Alright, so once we have this, then we can now write the piecewise function. The piecewise function for this Golden Corral restaurant, the piecewise function for this Golden Corral restaurant will be C of A is equal to, we write, this is called braces. Braces. We call it braces. Braces. In piecewise function, we just have opening brace. You know, it's braces, we use it as set notation, for set notation. In programming, we also use it in programming. This is in piecewise function, we just have opening brace. We don't close it. We just open the braces. It's in your keyboard. So this will be, we write that this is $0. $0. Okay? And we can put a semicolon here for 0 less than age less than or equal to 3. Now, folks, look at what I wrote. I didn't put less than or equal to no, because you can't say somebody is 0 years. Would you say somebody is 0 years old? Yeah, you can. Okay. Well, yeah. That's okay. 0 years. Since age is A in years, put this in years then. Okay. Put age is A in years, and then cost is C in dollars. In dollars. Now you can put your currency. You know. You can put your currency. Okay. Now, age is A in years, then C is cost in dollars. Then you can have somebody being 0 years old. That's fine. You can have somebody being 0 years old. 0 years and 10 months. Okay? 0 years and 11 months. Okay. So this means that from 0 years to 3 years, it's free. Cost is $0. See that? And then the next one, we have $5.99. I put a semicolon. Now, you mustn't put a semicolon, then this is one way of writing it. Later, we can look at other ways of writing it. We can. So one way of writing it is you put the function or the piece. This is the first piece. The first piece. Okay? The first piece. Piecewise. Pieces in pieces, or piecemeal approach. Okay, the first piece, and then this is the domain for the first piece, the interval. Then this will be from 4 to 8 years. So 3 is less than A, less than or equal to 8. Now, remember I said that each domain, the domain should not overlap. They should not overlap. Because if you come here and put 3 is less than or equal to, then the computer program would be confused. Okay, this is wrong. Because this 3 is included, the less than or equal to, this equal to means that 3 is included. 0 is included, and 3 is included. Remember, we defined this here now as that this is going to be A in years. So that's why I put 0. So this 3 is included, and this goes for this. Now I cannot have this because this means if the person is 3.1 years old, 3.2 years old, Okay, 3 years and how many months? If you have passed 3 years, you know, then you have to include here. From 4 years, because let's do this as years, you know, let's do this as years. From 4 to 8 years, pay $5.99. Let's forget about using ages as decimal. Now, the next one will be $6.99 for 8 less than A less than or equal to 12. And later we are going to, later on down the video playlist, we are going to do continuity and discontinuity of piecewise functions. Some piecewise functions have continuity, some do not. Later we'll discuss that, especially if you're going to take calculus, you need to know those. Now, this is the piecewise function here. That's it. You see how simple it is. You know, that's it. And you can just simply write a computer program that calculates this. So when the child comes, you say, what's your age? 7 years. Age, man 7. Then it brings out the receipt. You know, it brings out receipt that this child will pay $5.99. So let's do some quick questions, and then we look at some mathematical functions that are piecewise functions. And this is just a simple real world applications. I mean, we're gonna do more. You know, the next video we're going to do water bill, and that would be really extensive application of piecewise function. And we'll do more. You know. So, if I ask you this question now, let's say Peter is 3 years old. What will be the cost of his meal, excluding taxes? Because this is excluding taxes. This is excluding tax. So what will be the cost of his meal, excluding tax? 3 years old. So you check. 3 years old is in what piece? What function? Okay, has that interval? Because 3 years is in this interval. The domain here. The 3 is in this domain. Then you check what is the function that has that domain. And the function is $0. So Peter will pay nothing. He will not pay anything. He will not pay anything. So the cost is $0. Now what if I ask you, Mary is 7 years old. How much will be her checkout price, including taxes? Let's say Mary is 7 years old. So Mary's age, let's say Mary is 7 years old. 7 years old. And let's say the store, let's say the restaurant charges say 7.5% tax. What would be the checkout price? What would be the checkout price? Checkout cost. Or what would be the cost? Or let's say cost. Okay, what would be the checkout price for that? So you say A is 7. So in this case, A is 7. You look for the domain that has 7. And that is in this domain, this interval has 7. Okay? So this is the total cost. Let's call this total cost. Total cost. That's the checkout price. Will be what? So 7 is in this domain. So the basic cost of the meal is $5.99. Right? Let's do it here. Let's do it right here. So in this case, the basic cost of the meal for 7 years. Okay, A is 7 years. Basic cost of the meal is $5.99. $5.99. Now the tax, 7.5%. 7.5% of $5.99. So that is 7.5 divided by 100 is 0.075 times 599. Okay. Let's be fast, so let's use calculator for this. So you do 0.075 times 599. Now I can do this without calculator. Trust me, I can. Then you know to reduce the time of this video. So let's do it with this. So this will be 0. This is 0.44925. 0.44925. Please do not round till the final answer. When you are dealing with money, do not, even not just money, do not, unless you're asked to, round intermediate calculations. Please, if you are not asked to round, do not come here and round to 45 cents. No, do not. Okay? So now the total cost that she will pay is 599 plus 0.44925. So her checkout price would be 6.43925, and which is now $6.44. $6.44 would be her checkout price. Okay? Does that make sense? Please do not round until the final answer. Do not round intermediate calculations. No. You only round at the final answer. Alright. So that is that's just now the concept. At least you've seen the concept about piecewise functions. Let's discuss some mathematical functions that are examples of piecewise, because your professor might ask you to give a real-world application. This is a simple real-world application. Your professor might also ask you to list some examples of piecewise functions. Let's look at some examples of piecewise functions, and then we can call it a night. We're going to talk about three examples of piecewise functions, 3 mathematical examples. These are just real-world applications. Then when we do examples, mathematical examples of piecewise functions in mathematics. Just mathematical functions that are piecewise functions. The first one is the absolute value function. Absolute value function is a piecewise function. Okay. Then the next one we shall talk about is the greatest integer function. Greatest integer function or you can call it the floor function. Floor function. The next one we're going to talk about is the least integer function. Least integer function. Or you can call it the ceiling function. Ceiling function. Now these these are just some of them. This is not all of them. But let's focus on this. These two right here are also called step functions. are also called step functions. When we are going to do graph, when we do graph of piecewise functions, we are going to graph this, so you see why it's called step functions. And when you graph it, it's like steps. Their graph look like steps. That's why we call it step functions. They're also called step functions. So step functions are part of piecewise functions. Let's start with the absolute value function. Let's start with the absolute value function. Now, you know the absolute value function, you know that it is always, the absolute value of any number is always positive. You know, that's what, you know that, right? Okay. Now, you know the absolute value function, let's say, is this, of x. Okay? So, absolute value function is like this. So let's say this is the absolute value of x. Absolute value of x. Okay? Absolute value of x. So we define absolute value function is, it consists of, this is negative x, comma, if x is less than 0. And that's the definition, okay? And this will be equal to x, comma, if, so as you can see here, I'm writing this another way. The first way I didn't write if, I just put the semicolon and I just wrote the condition. I wrote the interval, okay? This second way I'm writing the function, I put a comma, then I put if. I mean, there are several ways to write piecewise functions. This is another way you can write it. So this will give us x if x is greater than or equal to 0. So you look at this here, and you can test this. You can test it. Let's say that x is less than 0 are negative numbers. So let's say maybe when x is negative 3. If x is negative 3, that means the absolute value of x will be negative x, because it falls in this domain. Negative 3 falls in this domain. Let me use a yellow chalk to color it. So negative 3 falls in this domain. So as you can see here, you look at what you're going to use this, because you use the function that has that domain for the value they gave you. You can't use it here. Okay, if you have negative 3, you use that the absolute value function is equal to negative x. And that will give us what? Negative 3. And that gives us 3. Because absolute value of negative 3 is still 3. Absolute value of negative 3 is still 3. So as you can see, that works. See, it works. And then when you come here, absolute value of 0. Absolute value of 0 is the 0. Absolute value of 3. Because 3 is greater than 0. Is 3. That's it. If you want to write it, absolute value of 0 is 0. Absolute value of 3 is 3. Because it's x. And that is 3. So you just use the one that corresponds to that. You always use the one that corresponds to you use the function that corresponds to the domain for the value you were given. If you're given 3, then you look at where does 3 fall? What domain? Does it fall here or does it fall here? 3 falls here. then you look for the piece or the function, sub-function or pieces that corresponds to this, that has that condition for those that fall in this domain, and then you use it. Okay, -3 falls here, so we use this. Yeah. Another example is the greatest integer function. The greatest integer function. So the greatest integer function is defined as the greatest integer, the greatest integer of a variable, say x. Okay, you can write it down. The definition is also here. Okay, the greatest integer of a variable, say x, is defined as the greatest integer of the greatest integer that is less than or equal to x. Okay, I repeat. The greatest integer of a variable, say x, the greatest integer function, let's say of a variable, say x, of a variable, say x, okay, can be written as this. We can write it as this. Can be written as this is a floor function, the floor. So we write it as floor. Look at the way I'm writing it, floor function, floor. Or you can write it like this. You can also write it like this with the double brackets. You can write that with the double brackets. The double brackets. So you can write it like this or like this. The greatest integer of x is a floor function. And we say floor because of the way we write it on the floor. Or you can write it like this with the double bracket. It is the greatest integer that is less than or equal to x. It is the greatest integer that is less than or equal to x. So how do we define this now? We write that the greatest integer function is also a piecewise function. This is equal to x if x is an element of the integers. This is element of the set of integers. This here means set of integers. This z, uppercase z, set of integers. Look, this is what I'm drawing. Yeah. This is a set of integers. Set of integers. If you have it like this is set of positive integers. If you have it like this is set of negative integers as a subscript. But just like this is just a set of integers. Okay? So we say if it's just an integer, the greatest integer will just be that integer. Okay? Now, it can also be x if you have, and I'm going to write some things here, if you have x dot y, in case of a decimal, okay, if you have x dot y to be greater than 0, if you have a decimal, and I'm going to define this in a moment, and then it will be x minus 1, it will be x minus 1, okay, for x, the decimal, x dot y less than 0. Let me explain what I just wrote. The greatest integer function. So let's say that this is a decimal. X dot y is a decimal. So x is the integer part. The integer part is x. That is what we are concerned about, integer part, x. So when we have a decimal, so look at what I mean here. The greatest integer function is just x if it is an integer. If it's an integer, whether it's positive integer or negative integer, it is just that integer, period. Okay. Then if it is a decimal, x dot y, it's good when you're writing this, please write it, that x point y is a decimal. Excuse me, x point y. Please, this is not x times y. You know, if it's times y, you do it like this. It's in the middle. The dot is in the middle. X times y. The dot product. That's the dot product. You write it in the middle. But if it's as decimal, it's x point y. X point y. It's a decimal, right? That is a decimal. So, for positive decimals, it's only x. The integer part of that decimal, which is x. And for negative decimals, you get the integer part and subtract 1. So let us look at examples of this. If you have, let's start with the first case. Let's say we have, what is the greatest integer of 3? 3 is an integer. It will give you 3. Use the 3. What is, excuse me. What is the greatest integer of negative 3? Negative 3. It gives you what? Negative 3. If it's x, if it's an integer, just put the value, period. Just put the value. If it's an integer, put the value. What is the greatest integer of 0? It still gives you what? 0. Okay? Now let's come to the next one. What is the greatest integer of 3.7? 3.7. What is the greatest integer of 3.7? Remember, we say that the greatest integer function is the greatest integer that is less than or equal to 3.7. The greatest integer of 3.7 is the greatest integer that is less than or equal to 3.7. 3.7 is a decimal. But what is the integer? What is the greatest integer that is less than or equal to 3.7? We can't have integer being equal to 3.7. 3.7 is a decimal anyway. So, but what is the greatest integer that is less than now 3.7 is 3. As you can see, if it's a positive decimal, just put the integer part, which is x. So this is 3. And still, it doesn't matter if you have 3.1. 3.1. Because some people might say this. If you have 3.1, it still doesn't matter. You ask yourself, what is the greatest integer that is less than 3.1? Because you cannot say less, in this case, the definition of greatest integer is the greatest integer that is less than or equal to that number. Okay? In this case, we don't have any integer that is less than 3.1, that is equal to 3. So you ask yourself, what is the greatest integer that is less than 3.1? The integer only, integer, is 3. So this gives you 3. Okay? Gives you 3. Then, let's do the negative decimals. Let's do negative decimals. If you have this, what is the greatest integer of negative 3.1? Of negative 3.1. So you ask yourself, what is the greatest integer that is less than negative 3.1? It is not greater than. Now remember in your number line, because some students make some mistakes in this, if it's negative decimals. In your number line, you have your number line like this. You have your number line of real numbers. 0 is in the middle. 0 separates the positive from the negative. So you have 1, 2, 3, 4. Then you have -1, -2, -3, -4. -4 is less than -3. -3 less than -2. -2 less than -1. -1 less than 0. 0 less than 1. See, as you move from left to right, it is ascending order. Ascending order from least to greatest. If you're moving left to right, it is ascending order, least to greatest. If you're moving from right to left, it is descending order, greatest to least. 4 is greater than 3, 3 is greater than 2, 2 is greater than 1, 1 greater than 0, 0 greater than -1, -1 greater than -2, okay? So you ask yourself, what is the greatest integer that is less than -3.1? Okay, of course it gives you -4. But if you want to do it with this formula that I just wrote, if you do it with this formula I just wrote here, you see x in this case, you have -3.1, x point -3.1, x point y. So your x is -3. Your y is 1. Your x is what we are concerned about. Your x is -3. So you now do -3, -1, -3, -1, and that is -4. You see, it's a piecewise function. See that? What if you have greatest integer of -0.7? -0.7. Okay? In this case, your x will be -0. -0, -1 is what? -1. Okay? That's it. That's it. What if you have -25.9? -25.9. It will be what? -25 minus 1. -26. See that? In this case here, x is 3. In this case, your x is 3 because x point y. So in this case, your x here is 3. But if it's -3.1, in this case, your x is -3, and you use that, or you can just do it by the definition. The greatest integer that is less than or equal to that number. The greatest integer of any number is defined as the greatest integer that is less than or equal to that number. That's it. Okay? So that's the greatest integer function. Now let's do the least integer function, and then we can call it a knife. Least integer function. Just gonna come here. Least integer function. Say x. See, this is floor. Floor is the greatest integer. Okay. Greatest integer function is flooring. That's the greatest integer that is less than or equal to x. Now, the least integer function, we call it ceiling. Ceiling. Now, in computer programming, some for the greatest integer function, you can have it as floor, x. And some here will have it as seal, x. Or some might say ceiling, x. So anytime you see this, it talks about greatest integer for the flooring, and then seal, C-E-I-L, or ceiling is the least integer. Okay. So this is denoted as this. We denote it as this. Ceiling, like this. Ceiling. Or you can do it double brackets but in reverse. You can do it double bracket but reversed. Reversed, double bracket, like that. Okay, the least integer function, this or this. Now let's go ahead and define this least integer function, ceiling. So the least integer function is defined as the least integer that is greater than or equal to x. The least integer function of x is defined as the least integer that is greater than or equal to x. The least integer of a number is defined as the least integer that is greater than or equal to that number. The greatest integer of a number is defined as the greatest integer that is less than or equal to that number. The least integer of a number is defined as the least integer that is greater than or equal to that number. Ceiling. The least integer that is greater than or equal to that number. So this will give us x if it's an integer. It doesn't matter. Once it's an integer, it's the value of that integer, period. Now if it's a decimal, if it is a positive decimal, okay, greater than 0 means it's a positive decimal, then this will give us x plus 1. It will give us x plus 1. That is the integer part plus 1. And if it is a negative decimal, it will just give us x. It will just give us x. Alright, let's test it. Let's test it. Okay. Can we test it? Can we test it? So, if we have the least integer of 3, it gives us 3. If we have the least integer of negative 3, ceiling, it gives us negative 3. Period. Okay? And please, these calculators, there are calculators for this, greatest integer and least integer and absolute value. The calculator, you will get it on this website, okay, if you want to play with it. And also some calculators for some of the applications that we're going to do. You will get it on that website. Alright, so least integer of 3 is 3, least integer of negative 3 is negative 3. If it's integer, it's just the value. Least integer of 0 is 0. Alright, now let's do the positive decimals. If we have least integer of 3.1, least integer of 3.1, it is defined as the least integer that is greater than or equal to 3.1. We don't have any integer that is equal to 3.1. So we can now say, what is the least integer that is greater than 3.1? What's the least integer that is greater than 3.1? The minimum integer that is greater than 3.1, you see, is 4. It's 4. Because if you have 3.1, when you have 3.1 like this, x point y, we're concerned about the x, the integer part. So x is 3. So you just now do 3 plus 1. 3 plus 1, and that is 4. So this gives you 4. If you have the least integer of 25.7, in this case your x is 25. In this case your x is 25. 25 plus 1 is 26. You have the least integer of 25.1, because some people might think we are just approximating this because it's 0.7. We don't know. Even the least integer 25.1 is what is the least integer that is greater than or equal to 25.1. So we don't have any integer equal to 25.1. So the least integer that is greater than 25.1 is 26. So 26. See that? Okay? Then, because here, if you want to do it by the formula, here is x is 25. So 25 plus 1, 26. Now, let's do the next one for negative decimals. Negative decimals, if you have, what is the least integer of negative 3.3? Okay, just put the integer part only. The integer part here is negative 3. It's negative 3. Okay, because it's the least integer that is greater than negative 3.3. The least integer, the least one that is greater than or equal to negative 3.3. And that gives you negative 3. Okay? Because negative 3 is greater than negative 3.3. Okay, remember what we said here. If you're going from right to left, is descending order. Negative 3 is greater than negative 4. And inside here, you will find the negative 3.3 here. Like inside here, you have the negative 3.3, negative 3.3, negative 3.4, negative 3.5, negative 3.6, negative 3.7, negative 3. So negative 3 is greater than negative 3.3. You have to set the least integer that is greater than negative 3.3. Okay, and that is negative 3. So, or you can just look at the formula and just put it that is just the x. If you have least integer of negative 30.5, it gives you negative 30. You have the least integer of negative 30.1, gives you negative 30. Okay, please, we will stop here for tonight. Please watch out for other videos. It is in a playlist. It's in a playlist. You can get on my website, any of my 2 main websites, and see the playlist. Or you can go to this website directly and see the playlist. And you'll see the links, videos links. Okay, please view these videos in the playlist in order. If you have any questions, please feel free to ask. Thank you for listening, and you have a good day.